So the next algorithm is click. We call it click. It is clustering in quests. Yeah, they just proposed this name. It was proposed in 1998. It is automatically identifying subspace of high-dimensional data space that allow better clustering than the original space. Click can be considered as both density and grid based. Yep. It depends on our perspective whether it is a density or grid, but we can see it as a grid based approach. That's why I put this one in the grid based approach. It partitions each dimension into the same number of equal length interval, and it partitions an m-dimensional space into non-overlapping rectangular units. So again, we can see another word, rectangular. A unit is dense if of the fraction of the total data points contained in the unit exceed the input model parameter. So this one, still we use the dense, the keyword dense, it means the density. So the density usually we can determine by ourselves, or there should be some parameters to say that it is density or not. But we don't use any parameters like dbScan. So the parameters we can define by ourselves. A cluster is a maximal set of connected dense units within a subspace. So the major steps is like this one. We can partition the data space and find the number of points that lie inside itself of the partition. And then we can identify the subspace that contain clusters using a priori principle. You still remember a priori principle? If you look at the association rule, in the association rule, we have this a priori principle. So we select from the smallest object, and then if you still remember when K, we define the item. The item, if it is 1, we want to check whether it is frequent or not. And then we will check the K equals to 2, whether it is frequent or not. So the superset and the subset. If the subset is not frequent, then the superset is also not frequent. So that idea is implemented also in the click. So a k dimension cell C, where k is higher than 1, can have at least L points only if every k minus 1 dimension projection of C, which is a cell in the k minus 1 dimension subspace, had at least L point. So this idea is the same with the a priori principle. Okay, if the subset is not frequent, then the superset is also not frequent. Okay, so that's the simple description for this long words. So we can say like this one. If a cell is not dense as in this subspace, then it is not dense in the k dimensional space. In other words, if the k minus 1, it is the subset is not dense, then the superset or the k-dimensional space is also not dense. We can identify the clusters. We can determine the dense unit in all subspace of the interest, and we can determine the connected dense unit in all subspace of interest. So dense unit, we need to check the density or the connected dense. That's why if you still remember in the first part, we have the density reachable, directly density reachable, and we have density connected. So the idea is the same. The first is we need to determine the dense unit. So the dense unit is about the density reachable. And the other is the connected dense unit. So it is the density connected. We need to generate the minimal description of the clusters. It means we need to determine the maximal regions that cover a cluster connected dense units for each cluster and determination of the minimum cluster for each cluster. Maybe it's better to see this data. In the first graph, we can look at this one. We have the salary and this is the age. And we can make the grid. So this is the grid. This is the grid. And if in the grid is, we can see there are some points in the grid, then we will use this grid. We will use this grid. And if you look at this grid, the determination of this grid is very subjective based on the number of the data that available. So in this grid, we have like the minimum description. The age is minimum 25 and is less than 45. So this is less than 45 here. This less than, it is higher than 25. And we want to check the salary. The salary is between 3 and 7. So we have the first grid. The first grid is between 3 and 7, and then 25 and 45. And then we have another option, or we have another criteria from 35 until 50, from 35 until 50, and the salary is between 2 and 6. So we need to make this kind of description, and the clusters will be based on this description. If we look at the density-based clustering, we need to define the parameters like the min PTS. We need to define the EPS. But with this kind of data, we cannot determine this one. So we can make our own definition. For example, this is using the minimum description. So this kind of minimum description can be applied to any kind of data. So if you want to apply to this data, then after you know this minimum description, you can look at different perspectives. Let's say I know that based on this minimum description, the age is between 25 until 45, and yeah, we change to the perspective here. We want to check based on the vacation. So how many weeks that employee took the vacation. And if we look at this one, we have another kind of minimum description. So you can set another minimum description to make the clusters. And then you can check whether this dimension has been dense or not. So after you have those, you can plot, let's say in this kind of dimension, you want to see from the perspective of age, and then you want to see the salary and the vacation. And you can look at this kind of graph. So dense unit found with respect to age for the dimension salary and vacation are intersected to provide a candidate search space for dense units of higher dimensionality. So if you already set the minimum description here, if you set the minimum description here, then later on you can find the higher level of the definition. So the strength is, we can automatically find the subspace of the high dimensionality, especially if we can see the high density clusters in the subspace. It is insensitive to the order of the records in input and does not presume some canonical data distribution. So I don't care whether it is normal distribution or whether it is uniform distribution, because I just use the minimum description. And it is linear scale with the size of the input and has good scalability as the number of dimensions in the data increases, because we just use the if then else rules, just using the minimum description. Weakness is, the accuracy of the clustering may be degraded at the expense of the simplicity of the method. It's very simple. You can just set the minimum description, but maybe for the company it is easy, but for the scientific purpose, we are not sure whether it is the better result or not, because it's very subjective. Okay, that's what I can explain about the algorithms until now. So you already learned partitioning methods, hierarchical methods, density-based methods, grid-based methods. Yeah. So those are chapters that you need to learn for the final exam. And before I forgot, next week, Thursday, we will have quiz. Okay. So please prepare. The quiz will be closed book. So you need to at least memorize. But because the question will be in the e-class, I think it will not be difficult. So the last chapter in this clustering is about how to evaluate. How to evaluate the clustering is we need to see the clustering tendency. Assess if non-random structure exists in the data by measuring the probability that the data is generated by uniform data distribution. So whenever we have the clustering, so we need to see whether there is a tendency of creating the cluster or not. Tendency. Let's say we have this data. Maybe this data is like uniform data distribution. If you look at this A, there's a tendency. Okay? based on the visualization, you can see there's a tendency. This is the tendency of the clusters. But in the B, the tendency is low. In the C, the tendency is higher, because you can look at this one. So this kind of tendency you need to evaluate beforehand. Visually, we can see from the visualization. And the idea of the evaluation is based on this tendency. There is one measure, we call it the Hopkins statistics. So this Hopkins statistics, given a data set T regarded as a sample of random variable, it determines how far away O is being uniformly distributed in the data space. So let's say we have points and points from P1 until Pn, and it is uniformly from D. So for each of the Pi, find its nearest neighbor. So we want to find the minimum distance where we have the phi. Phi is the point in the D. And also we want to find another point which is Q. So we have P and Q, and we want to find also the nearest neighbor for every Q with regard to phi. So after we have the X, we have the Y, then we can calculate the Hopkins statistics. So the Hopkins statistics here, we want to summation of the Y divided by the summation of the X plus the Y. So X is this one. It is related with the points P with regard to of P, and then the Y is another point which is Q with regard to the P. If D is uniformly distributed, then the Xi and the Yi, the summation of Xi and the Yi will be close to each other, and the H will be close to 0.5. So this one is closer to 0.5. If D is highly skewed, H is close to 0. If the value S is higher than 0.5, it indicates clustering tendency at the 90% confidence level. So they check the minimum distance, and we can use the Hopkins statistics to see the clustering tendency. There's another way to determine the clusters. We call it the empirical methods, or sometimes people say as the elbow method. In the empirical method, we want to see the number of clusters is equivalently, this one is equivalent. Equivalent means not exactly the same, but we can approximately. Approximately, it means the two. So it is not precisely, but we can just make an approximate. The approximate measure is the square root of n divided by 2. This is the approximate measures. It is based on the empirical method, and we can measure with the elbow method. elbow. Do you know what is elbow? It's elbow. Okay. If you look at our arm, so this one shows the high degree of decrement. Then we will check the turning point of the curve. We want to check the curve. If the curve is like this one, then this might be the good cluster. Like this one. So usually these two might be the candidate of the clusters. I can say that 2 or 3 is good. So sum of within cluster variance, I think if you learn from the K-means, you learn already the SSE, sum of square error. So we learn how to get the minimum error from the examples in the K-means. So we also have this one, within cluster sum of squares. So we can just plot. If the K equals to 2, this is the sum of square. If the K equals to 3, this is the sum of square. If the K equals to 4, this is the sum of square. If the K equals to 5, this is the sum of square. Of course, if the number of K is higher, then the sum of square will be lower. But we cannot choose the high K. If the K is close to n, it means we do not need clustering. Okay. So what we need to do clustering is to select based on the most degraded performance from the sum of squares errors. If it is the high slope like this one, then maybe this will be the best. Okay. So maybe 2 or 3. The ideal number of cluster is when a gradient of the sum of squares gets quite low. So if it is getting low, like this one, getting lower, okay, then this area is proper for our cluster. 2 or 3 or 4 is good. And this kind of method is very subjective. You need to check or you need to choose by yourself. There is another way we can do with how to determine the number of clusters. We call it, this is the cross validation method. We can divide a data set into m parts. So the first is use m minus 1 part to obtain the clustering model. So let's say I have the n data, okay, from 0 until 100 data. So I split into m, maybe it's into 5. From 0 until 20 is the first part. From 20 until 40 is the second part. From 40 until 60 is the third part. Okay. So we will use m minus part to obtain the clustering model. Maybe we use this data for creating the clustering. And then the remaining part, we will use it to test the quality. So the remaining part, we will use it for testing. So for each point in the test set, find the closest centroid. So we will make the centroid here. We will find the best centroid based on the k-means or with other methods. And then after we have the centroid, we use this test set and measure with this centroid and then select the best SSE. And we can select the closest centroid to measure how well the model fits with the test set. For any k which is higher than 0, repeat it m times. So in the cross validation, let's say we have k equals to 5. Then we select 5 partition. So this will be for the training and this will be for the testing. And then we can have another. This will be for the training. This is the testing and this is the training. So we can rotate like that one in the cross validation. And we can compare with the other quality measurements. For example, whether the sum of square errors is low or not. So we call this is the cross validation methods. We can have the measures for this clustering quality. We call it extrinsic and intrinsic. Extrinsic, intrinsic. Extrinsic, it is similar to the supervised. The ground truth is available. For example, the iris dataset. In the iris dataset, we know the flower name. Okay, we know that it is setosa. We know that it is versicolor. We know it is the virginica. So if we do clustering, we can check whether the cluster 1 equals to the setosa or not, or the cluster 1 belongs to versicolor or not, cluster 1 belongs to virginica or not. So we can check the clustering result with this ground truth, because this is the extrinsic. We have measure, we call it the cube precision and recall matrix. Intrinsic, it is unsupervised. The ground truth is unavailable. So we do not know anything. Like the example that we have about the second-hand phone. So last time we have the examples. We have only the camera pixel. And then we have the battery time. So what can we do with that one? No ground truth. So we can just check the cluster based on the visualization. So we can evaluate the goodness of the clustering by considering how well the clusters are separated and how compact the clusters are. So we use the silhouette coefficient. So this is the silhouette coefficient that you see in the orange. So there are, for the extrinsic methods, we have this is the quality measures. C compared to the CG. Okay. For clustering C, given a ground truth G, then we can measure it. So there are Q is the quality, is good if it satisfies the following 4 essential criteria. So this is the criteria. First is homogeneity. Homogeneity means the purer, the better. So for example, this is the clustering ground truth. This is the clustering result. Okay. G means the ground truth, and this is the, for example, the clustering result. Okay, this is the ground truth is like this. Then the result clustering is this one. The ground truth is actually this one, but the clustering result is this one. The ground truth is this one. The result is this one. The purer, the better. So if it is more likely with the homogeneity of the ground truth, then it is better. Cluster completeness. should assign objects belong to the same category in the ground truth to the same cluster. So if the ground truth mentioned like this, we have 4, we have 1, we have 2, we have 1, 2, 3, 4, 5, 6, 7. So we have 7 here. Then, yeah, this one, okay, it is completed. This one, it is not complete because it should be separated 1 and 2, but it is grouped. This one is completed. Backpack. It means putting a heterogeneous object into a pure cluster should be penalized more than putting into a backpack or miscellaneous or other category. For example, I know that this in the ground truth, this data, it is belong here. But in the clustering result, this data belong to another group. Then we need to give like penalty or minus value. Small cluster preservation. We can split a small category into pieces, but it is more harmful than splitting large category into pieces. So let's say if we have this cluster, the ground truth says like this one, and then you want to split this large because maybe the distance is a bit far, so you make it different clusters. So this is still okay. But if you select like this, this one actually is very close. But you make it into cluster. So if you make into this small category, if you make it into pieces like this one, it is mentioned it is more harmful. So it is not good. So if you have a very big category and then you split into small, that is still okay. But if it is already small and you want to make it smaller again, it is not good. So this is the 4 essential criteria for the extrinsic method. There's a method we call it B-cube precision and recall matrix. The idea is we have a set of objects O1 until On, and then C is the clustering on D. So we want to check the LO, it means the category of O given by the ground truth, and then the CO is the cluster. So let's say if you know in the data of iris, the first data is setosa, and then the cluster result is C1. The second data is versicolor. The cluster result is C1. So it is not matched. So we want to check this one, how many match and how many not match. Or we call this is the correctness. We want to check if it is setosa in the ground truth. I want to check whether it is in the clusters that is similar that is assigned to the setosa. So the methods we have precision and recall. Okay, I don't discuss this formula. Just easy to understand is I want to see how many of the correctness. If it is correct, then 1. If it is not correct, 0. The higher precision, of course, it is the more correct. And recall, the higher recall is also more correct. The silhouette coefficient. The idea of select coefficient is to check based on the distance. If we have a data set T, suppose T is partitioned into K clusters. So for every data O, we calculate AO as the average distance between O and all other objects in the cluster with O belongs. So we have AO. This is the average distance. The average distance between the object O and all other objects in the respective clusters. BO is the minimum average distance. BO is the minimum average distance from O to all clusters which O does not belong. So you can see this O is the minimum the O prime is the cluster that does not O belong, and this O prime, it is when the object it belongs in the same cluster. So we want to find the minimum average distance for the BO, and we want to find the average distance for the AO. After we have the AO and after we have the BO, we can measure the silhouette coefficient. So the silhouette coefficient is the BO minus the AO for that particular object divided by maximum of AO and BO. Because this is the compactness of cluster to which O belongs. This is the degree to which O is separated from other clusters. So the silhouette coefficient is between -1 and 1. If it is nearby 1, then the cluster containing O is compact and O is far away from other clusters. So we call this is good clusters. But if it is negative, then O is closer to the objects in another clusters than the objects in the same clusters. So it is bad cluster. Okay, I think that's all that we can learn from this clustering. Okay. So overall, you already learned many things in this clustering. You learn the basic idea is the similarity. So the concept of the similarity, you can see there are many concepts about distance, and distance. And it can be applied to many applications. So the similarity is very important for the clusterings. And clustering algorithms can be categorized into, you already learned partitioning, you already learned hierarchical, you already learned density, you already learned grid-based, and some other methods. K-means and K-matrix are popular partitioning-based clustering algorithm. Another, this is not the things that you learn. So for the hierarchical clustering, you learn about the Agnes and Diana, okay, agglomerative and diffusive. But we focus on the agglomerative. You learn about the DB-scan. It is the density-based algorithm, and you learn about the sting and click for the grid-based methods. And the quality of clustering result can be evaluated in various ways. Okay, so the remaining are the reference for the clusterings. Okay, any questions or comments?